Professor R. Asokamani, Director for Research and Development, Dhanalakshmi Engineering College, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
We had the earlier chapter, the bondings in solids. Now we move on to the next chapter, which is on crystal structure, and is the first lecture in this chapter on crystal structure, and the contents of this lecture will be as follows: formation of solids, lattice, translational periodicity, basis vectors, basis and crystal structure. Now we move on to the origin of the universe. You know the fantastic thing about the Big Bang theory, the first 3 minutes, the most important period, 3 minutes, we had everything in the state of plasma. Then we go to the fourth state of matter as plasma, then you have got a gas, a liquid, and then solid. So you first initially you think of the plasma, that is a collection of ions and negative and positive ions, and after cooling, when the universe got cooled or increase of pressure, it lowers the kinetic energy, reduces the interatomic distance, the dilute gas become a more condensed gas, thereby there is a reduction in the interatomic distance. From gas you go to a liquid, almost freely movable atoms and low compressibility, short interatomic distance. In a gas the molecules will be far apart. You know, in the case of a liquid, say water, the intermolecular distance would have been decreased, the shorter interatomic or intermolecular distance, spatial and temporal, you have got gas, then it goes to liquid state, then upon as time goes on you go to a solid state, and I told you the freely movable atoms, the short interatomic distance, and finally you have the spatial and temporal fluctuations in the short range order, spatial and temporal fluctuations in short range order in the case of a liquid. And in the case of solid, you know, the atoms will be regularly arranged, as I will be showing in the lectures to come. We will be talking about solids, the crystal structure in which they are the different solids are arranged, the various structures, and in a solid state there may be phase transformations with regard to the origin of the earth itself. Now there will be, you know, when you apply pressure or when you apply temperature to the iron in the earth, it may undergo structural changes, the phase transitions, structural transitions, the magnetic ordering will also change, charge ordering, and several other things such as superconductivity. Now all these things are related to the crystal structure, right. Okay. Let us now move on to the kinds of solids that you can have. Either the solids may be crystalline or non-crystalline. You take SiO2, you got crystalline SiO2, wherein you got silicon bigger atom and the oxygen atoms here. Okay, you got silicon and oxygen in a crystalline solid, wherein you got periodicity. You see a hexagon here, the same hexagon is repeated here, the hexagon is repeated here, or the atoms are arranged in a periodic fashion. Whenever the atoms are arranged in a periodic fashion or a repetitive manner, the material is called a crystalline material, a crystalline solid, it is a crystalline, right. Wherein in a amorphous solid there will be no periodicity, there will be no regularity, there will be no repetition of atoms, right. You see here, upon quenching, upon rapid cooling, you get a amorphous or non-crystalline SiO2. The former, the first one is the crystalline SiO2 here, which is shown here, where there is ordering, right. You got a hexagon and hexagon, the atoms are arranged, silicon and oxygen atoms are arranged in a regular order, wherein here you do not have regularity. You see a bigger region and a much bigger region, a smaller region, there is no regularity here, right. There is no ordering. Whenever there is no ordering, that means it is a non-crystalline material. SiO2 is silicate. Now, you know silica, right. Silica is a glass. Glass is a amorphous solid, rubber is amorphous, bakelite, chalk, they are examples of amorphous materials. There is no periodic arrangement of atoms, whereas in the other hand, on the other hand, you have got very many metals and alloys and compounds. You take a metal like simple metal like aluminum or nickel or copper, or alloys like Ni3Al, Ti3Al, or compounds like NaCl, MgCl2, wherein there will be Na and Cl and Na and Cl. In the case of the lectures on bonding, you have already seen how the Na ion will be surrounded by chlorine ions, Cl ion will be surrounded by sodium ions. Now, there will be a regularity in the arrangement of ions, right. So, a periodicity will be there. A material is said to be crystalline if the atoms are arranged in a periodic manner, right. There is a regularity in the arrangement of order, in the arrangement of atoms, that is called a crystalline solid. Now, therefore, as I told you regarding the origin of the universe, or you take a molten material and you transform it to a solid state, a molten, if you have molten iron, you put it in a container. Now, this is a molten liquid, right, the molten material, and what you find is when it starts initially when you are poured into a container, there are certain points where the what is called nucleation starts, solidification begins. There are certain points where entire thing is a liquid, but you have certain points where nucleation starts, small nuclei, a collection of fewer atoms will be there, and around a particular atom there will be what you call a few atoms will be gathering, and they are called a nuclei, right, and the nucleus will grow in size. So, these nuclei they start growing, right, the crystals that will form, and they are called grains, right. The remaining region is still in the liquid state, right. As more time elapses, finally the entire liquid is converted into the solid, but the important point is in every solid material, right, you take a piece of gold or a piece of iron or whatever material that you got in a periodic table, all metals if you take, they will be having what are called, there will be arrangement of atoms in a regular order, that is called a grain. What is a grain? Grain is a region where the atoms will be arranged in a regular manner, that is a grain. Now, there will be what are called grain boundaries, right. they are called grain boundaries. There are certain regions, this is a grain boundary. In the grain boundary, the atoms will be disorderly arranged. There will be no, there is a region where a few tens of angstroms thick, where there will be no order. Here there will be no order, right. Again, this is another grain, there will be order here, there will be the atoms are arranged in an orderly manner here, the orderly manner here, again orderly manner here, but the orientation of the atoms that you got here in this grain and in this grain, their orientations may differ, will differ. So, anyway, there will be ordering here, there will be ordered arrangement of atoms here, the ordering will be here also, but the ordering will be in a different orientation, and there will be again ordering here in this grain. So, there are grains, they are called grains, and these are grain boundaries where there is a disorder, right, grain boundaries. Therefore, the A refers to the formation of stable nuclei and B refers to growth of nuclei, the nucleation growth. It is very famous, the wordings, the nucleation and growth, lot of thermodynamics comes here, whether the nuclei that is formed, will it be stable, how far, that should be a critical radius above which only the nucleation will the nuclei will start growing, the nucleation and growth. The nuclei, they start growing, leading to small crystals here, and this is tiny crystal, this is again a tiny crystal, right, that will be order here. So, there are tiny crystals or grains and followed by what are called grain boundaries, a disorder, right. And in the next slide you will again see the tiny dots show the nuclei, and so again a nuclei here, the formation of small bigger nuclei, right. So, you got bigger nuclei, and from A you go to B, the growth of these nuclei into small crystallize. What do you observe now? The crystallize here, there is order, right. The arrow along which I move, the unit cell I will now call unit cell, or the arrangement is orderly, right. You got, there is order, and similarly here there is order, right. The building block or whatever that you got a square, the squares are orderly arranged, the squares are orderly arranged. So, this is a crystal, this is another crystal. So, from small nuclei you go to slightly bigger nuclei, the nuclei they start growing, they give rise to bigger crystals, and from bigger crystals you go to much bigger crystals, right, much bigger crystals. Now, where are the grain boundaries? You see here, the repetition is there, right, the squares are repeated or the atoms are arranged in a periodic manner here, but there is something goes wrong. If the entire thing is repeated throughout the volume, it is called a single crystal. What is single crystal? For certain specialized applications, scintillation counter, some nuclear detectors, you need single crystals, right. Single crystals are for special applications. What is a single crystal? You have got atom here, atom here, atom here, the atoms are periodically arranged throughout the entire volume. For throughout the entire volume of a crystal, if the atoms are periodically arranged, it is called a single crystal. Is it a single crystal? This is not a single crystal. You have got a grain here, you have got a grain here, there is order here, there is again order here, but you see the way in which the atoms or the cells are arranged, it is orderly arrangement is there in this region, but again there is orderly arrangement, but something goes wrong here in between, right. So, this is a polycrystalline sample, whereas a single crystal is one in which there will be order. You see the grain boundary here, right, there is a grain boundary. A crystal is nothing but a arrangement of atoms, and we have been talking about crystalline material and non crystalline material and how crystals are formed. I told you the solidification formation of polycrystalline materials, this is a polycrystal, right, this is a polycrystal as against a single crystal. If this would have been followed continuously throughout the volume, throughout this entire slide, it would have been called a it would have been a single crystal, but that is not the case. You have the pattern like this. Here this pattern, the orientation is different, right. So, this is surely a polycrystalline sample. Now, between the grains, okay, you have got, or the crystallites, you have got some kind of misorientation. You do not have this region is called a grain boundary, right, called a grain boundary. As I told you earlier, the grain boundaries were there, and now this is the grain boundary, right, these are the grain boundaries. Okay. Now, this is a crystal here, this is a crystal here, there is a grain boundary, right, this is a grain boundary region. Okay. And you may ask the question, why should you study the chapter on crystal structures, or what is the importance, why should one study, what motivates you to study the crystal structure. Now, the study of the crystal structures using X radiation, I told you that crystal structures can be studied using X-ray diffraction. We have seen the Bragg's law and so on. The positional arrangement of atoms can be studied by X-ray diffraction. By studying this positional arrangement, or by knowing how the atoms are arranged, what is it you are getting? By studying the crystal structure along with the nature of bonding, right, how the the atomic arrangement plus. Now, where from you get these electrons? These electrons are coming from the valence electrons of the atoms. Therefore, the important point is the following: the position of the atoms along with the fact that how the electrons are arranged to bind the atoms that you have got in the solid. These two together will decide the properties. What properties? The physical, chemical and biological, all the properties of non-living species and living species, non-living the normal materials and living biological systems, living species, all these things are governed by the two factors, the structure and bonding. The very important thing, the crystal structure and the bonding means what? How the germanium atom here and another germanium, they are bonded to each other by means of the electrons, how the electrons are distributed between two germanium atoms. This is the crystal structure of germanium. So, the motivating factor as to why one should study the crystal structure is, along with the crystal structure, if you know the bonding, many of the properties of materials are determined by the arrangement of atoms and the bonding behavior or bonding nature. The arrangement of atoms in space is called the crystal structure. This is one arrangement, right. You have got there is a regularity, right. There is a arrangement of atoms in the most important semiconducting material like silicon. This is how the atoms are arranged, right. The arrangement of atoms in silicon or germanium. I told you in the last series of lectures on bonding, after 1960 silicon has taken over germanium, SCR, silicon rectifier, and MOSFET, many things, many electronic components which are used in computers and so on are based on silicon. So, this is the crystal structure of silicon. The bonding in silicon or germanium, both are the same. So, silicon and this is germanium atom here, germanium atom here, the electrons that you are having here, they give rise to the bonding, they explain the bonding, the covalent bonding. So, along with the position of the arrangement of atoms, namely the crystal structure and the bonding, all the properties can be studied. I mean the properties means electrical, thermal, optical, magnetic, superconducting, all the properties. I will be talking about phonons, the atoms in solids, they are vibrating in the end of the chapter. Now, that gives you explains the phenomenon of superconductivity. Therefore, when you want to explain the various phenomena or various properties of solid materials, the physical properties, chemical properties, and not only materials, the living tissues, the biological systems, then there are also DNA, so many other things. Then in all cases the arrangement of atoms as well as the bonding that exists between the atoms, they are very important in order to understand the properties. So, you pass on to now crystal structure. How do you explain the crystal structure? The basic thing one should understand are the three words. What is meant by a lattice? Then the other words, basis, the crystal structure. The terminologies which are to be understood are lattice, basis, crystal structure. So, what is crystal structure? It is nothing but you have a lattice, lattice plus basis gives the crystal structure. What is a lattice? It is an array of points in space. You visualize in space, it is imaginary network of points in space. You got a point here, you got another point here separated by distance a, another point here separated by again distance a, or the distance between these two will be 2a, then 3a, 4a, and similarly you got, so a here, then a here, and similarly you can have a here or b here and then b here, and so you translate this point from here to here, translate it from here to here, and so on. Similarly, you translate it from here to here and generate network of points, a set of points in space where there is regularity or there is a perfect arrangement, a regular neat pattern, a repetitive pattern is there, right? A repetitive pattern is there. This is called a lattice, right? A lattice, this is called a lattice. Then this is called a basis. Basis refers to what? An atom or a group of atoms, or an ion or a group of ions, right? That gives what is called a crystal structure. This is a crystal structure, right? Okay, in two dimensions. I will tell you more about it in order to that you have a very firm footing or understanding of crystal structure. Now, you see a lattice here, right? A network of points, and a collection of points, an orderly arrangement of points, right? A very important point. An orderly arrangement of points here. You got a point here, point here, point here, point here. They are orderly arranged. Then this is the basis, right? Now this is a basis. Now you put the basis at the lattice point, right? The basis now has only one atom. Suppose the basis is copper. How do you get the copper crystal, copper structure? So you have only one atom, right? The copper atom in the monatomic solid, same kind of atoms. So the basis contains only one atom, right? Now this is the copper atom. You put the copper atom on the basis, right? You got a basis. You see the green here again. So the copper atom, the atom is kept here. Now again you see the green, the lattice. On the lattice you put the basis, right? You got copper atom. So this gives the copper crystal. Now on the other hand, the basis having one atom, you got two atoms here, right? The basis contains two atoms. You got a one circle and one something like a rectangle, right? Then where do you have two atoms? You take NaCl. What is the basis? It is Na ion and Cl ion, right? In the case of copper, it is a monatomic. The entire crystal is made up of only copper atoms, right? In the case of copper, you have a lattice here. Then you put the copper atom at every lattice point. You put the copper atom. Okay. Then you get what is called the crystalline copper. This is crystalline copper. On the other hand, if the basis contains not only one atom but two atoms, or you may have more atoms, you take barium titanate. What is the basis? BaTiO3. Basis contains one barium atom, one titanium atom, then three oxygen atoms, right? So if you have got a compound like barium titanate, then the basis becomes more complicated. But take the case of NaCl, a simple case. I mean two kinds of atoms, Na and Cl. You assume this to be Na and this is Cl, then these two should be kept along the lattice point. You see here, the lattice point is here, Na is here, Cl is here, right? Lattice point is here. About the lattice point, you have to put the two ions, right? About the lattice point, you have to put the two ions. The ions are here, Na and Cl, right? Or you have got two atoms or two ions, right? Na and Cl. Now, these things are to be very clearly understood, right. What is the basis? One should not be getting confused when you have got more than 2 atoms. How do you visualize the crystal structure, and where do you keep the atoms? I will strengthen my argument by showing this slide once again. You have got a 3-dimensional periodic array of atoms or molecules. This is a space lattice, a regular periodic arrangement of points in space. You see here there is periodicity, right. You got a periodic arrangement of atoms, right. You all agree that there is a periodic arrangement of atoms. Periodic means A, 2A, 3A, 4A, 5A, and it is a square lattice, again A, 2A, 3A, 4A. Okay, the periodic, it is a square lattice. What I do now, with this lattice I attach a basis. Now, the basis now contains 2 atoms, right. The basis, this is the basis, atom A and atom B, or ion A and ion B. One may be Na ion, the other may be Cl ion. So, you have got the basis contains 2 kinds of ions, right. So, you have got positive ion and a negative ion, or 2 kinds of atoms. Okay. And now, I am showing clearly atom A here, atom B here. Now, the atom A will be kept here, atom B will be kept. The lattice, where is the lattice point? The green will be at the center, right. Green will be at center. So, about the lattice point you have to put the 2 atoms. If there is a ternary system, then you have to keep the 3 kinds of atoms about the lattice point, right. So, the basis contains 1 atom or 2 atoms, a group of atoms, or a group of ions. In the case of sodium chloride solid, you do not have atoms, you have got ions, Na ion and Cl ion. So, the Na ion will be kept here, Cl, the bigger ion will be going here, right. The lattice point will be here. So, about the lattice point you have to put the ions, right. This gives the crystal structure, as I am indicating here. NaCl structure, sodium chloride crystallizes in the FCC structure, as all of you know. The basis consists of a Na and a Cl atom, right. You got a Na and Cl atoms or Cl ions, right. These fundamental things are very, very important, right. Then when you talk of the 2-dimensional lattice, this is called a lattice, right. What is the lattice? Periodic arrangement of points. You do not talk of atoms, a periodic arrangement of points in space is called a lattice. Okay, now, you see a periodic arrangement, right, of points here. The repeating pattern of atoms, the first you got a lattice point here, a lattice point here, lattice point here, lattice point here. This A, the vector A is called a primitive translation vector. Why it is called translation vector? I can, as I told you earlier, A, you can have 2A, 3A. So, this lattice point, from this lattice point you can move to this lattice point. You can generate the entire lattice, right. You got a 2-dimensional lattice by repeating A, and similarly these lattice points, your lattice point here, the lattice point here, these lattice points along this direction can be repeated by translating B. So, A and B are called the primitive translational vectors. By repeating these translation vectors, you can generate the entire lattice. Now, we will move on to the summary of today's talk, and the summary will go on like this. Crystal structures have a bearing on the physical properties of solids. All lattices have the property of translational invariance, and the questions that we have are define lattice, basis, and unit cell. The question number 2 will be what is meant by translational invariance. With this we come to the end of lecture 1, and the rest of the things we will see in the lectures to come. Thank you.